Okay, the last type of electron configuration that we need to talk about is what's known as dot notation. And to introduce dot notation, let's review some of the ways that we've represented electron arrangements prior to that. And so I'm going to use the element sulfur as our example. Let's go back to sulfur that we started out the videos with. And so here I've got the orbital notation for sulfur. So I've got energy levels along the side, I've got sublevels listed across the top, and the individual orbitals are listed here. And then I've got arrows that represent electrons, the direction shows the spin. It clearly shows me things like I've got two unpaired electrons here. I've got a set of paired electrons in this 3p sublevel. So it shows me those sorts of things. It would show me if I had any empty sublevels, all those. But it's a little bit of much to write out all the time. So we do electron configuration, which we learned how to read from the periodic table, like 1s2, 2s2, 2p6, 3s2, 3p4. And then we said, okay, well, that could be a lot to represent. So let's just focus on those, what we would say, the last sets of electrons to go in. So we do shorthand notation. We go back to neon here, and then we just write the last row, you might say, of things that we need to fill in. So it's neon 3s2, 3p4. Now, dot notation is even more condensed than that. It's very useful because we use dot notation to draw structures of how molecules, where you take atoms and bond them together, are represented. The dot notation starts out with this. We use the symbol for the element, so S for sulfur. And that, you can think of that as kind of like a picture of the atom. That's the nucleus of the atom, and that is all of the inner shell electrons. So one thing with dot notation we have to remember is that there are inner shell electrons and there are outer shell electrons. And dot notation only represents outer shell electrons. And so let's take a look. What are the outer shell electrons that we have to represent? Well, those are electrons in the highest energy level. So all of these are outer shell electrons. So somehow in our dot notation, we just want to use dots to represent only outer shell electrons. If we were looking at electron configurations, the outer shell, that's not this here, because the outer shell is the third energy level. So it'd be any electrons here after. So these are all inner shell. And so it's just those electrons. And then notice that the shorthand notation is only really showing us, in this case, the outer shell electrons. When we get to the D block, you might remember that wouldn't always be the case. But so we just have to represent outer shell electrons. Well, how many do we have? Well, we have 1, 2, 3, 4, 5, 6. So we're going to put 6 dots in our dot notation. Think of this as like I could put 2 dots on each of these 4 sides of a box that go around there. So I go 1, 2, 3, 4, 5, 6. Now the order that you could start here and go that way, whatever, it doesn't matter, as long as you're not like bunching them all up and you only put a maximum of 2 to a side. Typically you go like 1, 2, 3, 4 and then kind of double them up, but that's not super important. So that's the dot notation for sulfur, and so that represents just the outer shell electrons. Now, you might remember this full half-full rule, and noble gases, the reason that they're so stable is because like neon has a full S with 2 electrons and a full P with 6. That's 8 electrons in its outer shell, and it turns out that's really stable. The nice thing about dot notation is you can clearly see whenever you're nearing 8 electrons in the outer shell, you can see that sulfur has 6. If it only had 2 more electrons, it would be really stable. Now there's a quick way to do dot notation reading it off the table, and that's by looking at the family. So I've labeled this as like 1A, 2A, we'll skip the middle for a minute, 3A, 4A, 5A, 6A, 7A, 8A. That tells you how many dots in that notation. So sulfur is in family 6A, and all the elements in family 6A have 6 electrons in their dot notation. So I could put sulfur with 6. So let's do some more dot notation. So let's say magnesium. Okay, Mg. Well, here it is, and it is in group 2A. That means it has 2 outer shell electrons, and so 2 dots in its dot notation. Okay? Well, let's come over here to krypton. So let's do krypton, Kr. Okay, well, krypton is in group 8A. That means 8. So here it is, 8A. It has 8 outer shell electrons. So I'd go 1, 2, 3, 4, 5, 6, 7, 8. Okay. How about aluminum? So here's aluminum. Okay, it's in group 3A, so it has 3 outer shell electrons. So 3 dots. Okay, let's do iron. Fe. Now iron is in the D block, and for most of the D block, other than copper and chromium, which we mentioned last time, they're going to have 2 outer shell electrons. That's because, like for iron, it puts 2 electrons in the 4s, and then the extra electrons, it doesn't put them in the outer shell, it puts them in the 3d. That's an inner shell. It's not the outermost energy level. So all of the D block, except for copper and chromium, think of them as having 2 outer shell electrons, like that. So this is dot notation, and dot notation is a real handy way to represent outer shell electrons quickly. There's something, so I've mentioned some terms. So we've talked about inner shell electrons. We've talked about outer shell electrons. And then there's another term that you'll sometimes see. It's called valence electrons. And valence electrons refer to any electrons that can be involved in chemical bonding. Normally those are outer shell electrons, however, sometimes some of those D electrons count as that. But when we're representing dot notation, we're only representing outer shell electrons, and so those are the ones in the highest energy level. And you can look at the family to tell you how many dots go in the dot notation. So you got 1, 2, this with 2, and then 3, 4, 5, 6, 7, 8 dots in their dot notation. Okay, so that completes all of our ways that we represent electron configurations.